Good afternoon, everybody. My name is Alex Plotkowski. I am a staff member at Oak Ridge National Lab in the Materials Science and Technology Division. I also work at our manufacturing demonstration facility where we do a lot of research related to advanced manufacturing technology. I'll be talking today about controlling microstructure using additive manufacturing. So the reason that we're interested in controlling the microstructure is obviously because the properties of our materials are dependent upon the structure that's formed during manufacturing. So here I'm showing an example of Inconel 718, a nickel-based superalloy, and we've got two different microstructures here. One which is equiaxed with random distribution of grain orientations, and another one that's columnar with a strong preference for the 001 direction of our grains to be oriented along the build direction. So if we take a look at the tensile behavior at room temperature for these two microstructures, our properties are dependent in the columnar case on which direction we're pulling. So if we pull along the direction of the grains, along the build direction, we get a slightly higher yield strength. And if we pull transverse to that direction, then we get a lower yield strength. In the case of these equiaxed grains, we get similar properties no matter what direction we pull. So if we were interested in trying to design, say, I don't know, a turbine blade where our stresses are strongly oriented along a particular direction, we may prefer a columnar set of grains with the grain orientation along the loading axis. However, if we have a more complex stress state, perhaps we would prefer more randomly oriented grains with a more uniform distribution of properties. So early on, we did some work, and this is actually before I joined the lab. This is a colleague of mine, Ryan Dayhoff, did some work trying to show that we could use different scan patterns to get different grain orientations in different regions. However, this kind of early work was imperfect. And so if we take a closer look at these different regions, it's not that we have a purely equiaxed or purely columnar. We very often get more of a mixed microstructure in different regions. So the main question for the work that I'm going to be showing today is how can we improve the overall process capability so that we can get better control of our microstructure. So to achieve this kind of variation in microstructure, we've been working on developing these kinds of unique scan patterns that allow us to get different microstructures with different sets of processing conditions. Really, the goal for this is to be able to adapt it to any kind of geometry. So this is an example of some work done by a summer student named Chris Arthur, where he did a finite element model for a simple bracket and showed that we could get better performance if we had equiaxed grains in some regions and columnar grains in other regions. However, it's quite challenging to be able to do this for these complex geometries. So we have to take a closer look at how to be able to predict these linkages between process and microstructures so that we can design processing strategies to give us this distribution of microstructures that we're most interested in. So in this case, I've been talking about Inconel 718 and particularly looking at columnar versus equiaxed types of grains. So the first thing we need to understand is what controls that type of grain formation. And that comes down to this kind of simple model for growth of our columnar dendrites competing against the nucleation of new equiaxed grains. So there are models for this, and here I'm picking out a relatively simple phenomenological model originally proposed by Hunt. I've got it here as it was summarized in Danzig and Rapaz's book. And essentially, we can write down rules for the nucleation of new grains as well as the growth of existing dendrites. And by kind of pitting these things against each other, we can create a process map that tells us where we're likely to get different types of microstructures. So when our thermal gradient is very high and our solid-liquid interface velocity is low, we're more likely to get columnar dendrites. Whereas if our interface velocity is high and the gradient is low, then we're more likely to get equiaxed grains. So the key thing here is that the things that we need to know is what is the solidification interface velocity at the solid-liquid interface, as well as what is the temperature gradient. So this really suggests that what we need is a process model that relates our processing conditions to these types of conditions at the solidification front. So what do we need in our process model? Well, there's a lot of complex physics that are taking place here, as I'm sure many of you are aware. We have the heat source interacting with the material, and there's absorption and reflection going on. Very near here, we've got radiation as well as convection effects from Marangoni surface tension effects driving flow within the melt pool. There's also evaporation going on, as well as melting, solidification, latent heat effects, and conduction out through the surrounding material. So it is possible to put together models that capture different levels of this physics. The thing that I want to make clear here is it's depending on what it is that we want to to model, it's really important to select which types of assumptions are okay or not okay for our particular purposes. So it's actually quite an important thing to determine which type of model or which set of assumptions are most suitable for your problem, because the variation in how expensive that computational model is varies quite dramatically. So Jerry Knapp put this kind of timeline together for me where we're looking at the range in expense of a particular model measured as the number of CPU hours required to simulate 1 millimeter of melt track for different types of models. And so all the way on the far right end here, we've got things that are resolving the powder and the free surface effects of our melt pool. And all the way at the other end, we have something that is essentially only modeling heat conduction in a semi-analytical sense. And you can see that there's roughly 9 orders of magnitude difference in the computational expense to span these different sets of assumptions just for models that are ostensibly simulating roughly the same situation. So for here, what we're going to do is start somewhere here in this kind of continuum melt pool scale model and see whether it's suitable or not for understanding our microstructure control problem. So we've developed a model for this purpose. This particular one is built on open foam, and it includes a volumetric Gaussian heat source that we can apply, and we can have any arbitrary scan path, as well as evaporation, radiation, etc., as well as the fluid mechanics. So I'm showing here some validation against some laser weld tracks done by NIST on Inconel 625 plates. Here I'm showing that if we turn on the fluid mechanics and calibrate it correctly, we can get quite decent agreement with the experimental melt pool shapes. For cases where the fluid mechanics isn't too important, even though just the conduction only model works reasonably well. And from this type of model, we're able to extract the types of solidification conditions that we care the most about, in particular the thermal gradient and the velocity. I'm showing a couple of comparisons here for different cases. One thing to note is that as the Peclet number gets higher within your melt pool, that means that the fluid mechanics is more important. So we see more of a variation in the model predictions, depending on whether we include fluid mechanics or not for these cases where the fluid flow is quite rapid. So we've taken this model and now I want to apply it to the particular case of the spot melt scan patterns that we're using for these electron beam processes. Here we're going to take this complicated spot melt pattern and simplify it by isolating just a single spot melt. We could perform a 3-dimensional simulation that takes a look at the kinds of conditions that we see for one of these spot melts given a set of processing conditions. In this case, we are including the latent heat and heat conduction, but we're ignoring fluid flow for now. And we can extract from here the types of thermal conditions that we care about. You can see here this kind of characteristic pattern where at the beginning of solidification near the edge of the melt pool, we have high thermal gradients and low velocities. And at the later stages of solidification, we kind of dip down into this equiaxed regime and start to have these higher velocities and lower gradients. However, there is an issue. If we take a look at running this model over a variation in process conditions, we can get a distribution of grains that's either fully columnar or fully equiaxed. And indeed, experimentally, we can see those types of differences as well. But it turns out that we can't achieve this type of equiaxed grain structure under realistic conditions. So in this particular case, to achieve this fully equiaxed structure, the preheat temperature of the system was at 1528 Kelvin, which is actually very close to the solids temperature for Inconel 718. So the model is giving us some insight into the process and the ways that things vary with different processing conditions. However, it's not predicting appropriate microstructures under realistic processing conditions. So to explain the kind of issue that we're having here, I'll show another example. In this case, I'm showing 2 sets of kinds of microstructures that we achieve using these types of spot melt patterns. But these examples that I'm showing here on the left were achieved for just changes in processing conditions for a 20 millimeter cube geometry. So here's one build that we did where we did a range of processing conditions, but we did both 20 millimeter and 40 millimeter cubes. We applied the same scan pattern in these, and these numbers here are energy density or average energy density values, basically representing the type of scan pattern that was used. And so this part 5 here is a 40 millimeter cube that used exactly the same set of parameters as part 2, which is a 20 millimeter cube. And yet when we look at the microstructure, we see that the grain structure is dramatically different, that the larger component tends to give us more of a columnar type of microstructure, whereas this smaller component gives us a equiax microstructure. So it's really clear that our microstructure here is not just dependent on our process conditions, but also on the geometry of the sample that we're fabricating. Okay, so let's return now to our range of types of process models that we might use. So we started out in the middle here, and it's looking like what we have to be able to do is account for these larger variations in geometry, which means that we have to go to a lighter model and sacrifice some of the physics, and then that allows us to be able to simulate even larger areas, larger components. So now we're going to move this way towards this kind of semi-analytical heat conduction model to see if by simulating larger components, it's able to capture those types of effects. So perhaps the most obvious model in this case would be Rosenthal's model, the simple closed form solution for a quasi-steady point source going in a single direction. One example of this is the work by Gauman, where he was doing welding on single crystal substrates, and he was able to use this Rosenthal model to correlate his processing conditions to whether he formed a single crystal weld or formed all of these stray grains. However, for our case, the quasi-steady approximation of the Rosenthal model is quite limiting, so we'll have to look at a model instead that allows us to at least have some of the transient behavior of the complicated scan paths that we're interested in. So this is the model that we decided to use. I'm not going to spend time on the math, but we've adopted it from the multipass welding literature. Essentially, you have to perform this integration over time where the integrand encodes the position of your scan path. You end up having to do this as a numerical integration, so we've designed an adaptive integration scheme and some parallelization approaches that allow us to do this as quickly and efficiently as possible. And what that lets us do is, even with relatively modest computing resources, we can compute relatively large domains and complicated scan paths. And then we can also parallelize this on high performance computing platforms, as well as using GPUs or combinations of CPUs and GPUs. So now let's apply this to an example of some of these spot melts. So I'm picking out two particular samples labeled cube 15 and 16 here. The only difference between these processing parameters for this scan pattern is how long the electron beam is staying at each point. So in the left, we're using 0.1 milliseconds. On the right, we're using 0.25 milliseconds. And so over here on the left in cube 15, you can see that each of these spot melts is remaining pretty consistent throughout the scan pattern. But over on the right, we're building up a lot of heat in the sample, and that's allowing these melt pools to grow and eventually overlap. And we form this quite large melt pool throughout the entire cross-section of the sample, which then collapses at the very end. If we plot what our simulation conditions are now, we can see that this actually agrees quite well with experiments. So those variations in processing conditions give us several orders of magnitude different in terms of our thermal gradient and solidification velocity. And for the samples that were actually fabricated with those conditions, I'm showing the pole figures here. And you can see that they mostly match up with experiments as well, whereas cube 15, firmly in this columnar region, we're getting a very strong fiber texture in the 001 direction that's parallel to the build direction in this case. Whereas in cube 16, we get a much more random texture, although there are a few points that dip into this columnar region, and that's giving us kind of a mild fiber texture as well. So now I want to talk about how we can use this type of simulation technique to design new scan patterns that avoid this kind of geometric problem. We've designed a particular type of algorithm here that's meant to control the microstructure and balance between different regions. We've written a paper on this, so you can go see the actual algorithm if you'd like to, but I don't want to spend time on it here. At its core, it's kind of this stochastic probability weighting where we're picking these two different regions and trying to decide which point we want to melt next. What this ends up doing is giving us these very kinds of organic types of scan patterns where we're selecting locations to melt within our geometry that kind of conforms dynamically to the local shape of the geometry that we're interested in melting. And so what we do is we're able to kind of generate these types of scan paths. I can show you the types of probability distributions that were used to do that based on the local geometry effects. And then we can balance the scan paths between multiple regions so that the order that we melt points is kind of distributed in such a way to control the heat transfer effects. And we can tune this and test it using some of these same models. So here I'm showing what the predicted equiax fraction might be for these different regions here. And you can see that we're much more likely to get a very high equiax fraction in the center of this oak leaf shape than we are around the borders. So far, this is just showing you kind of a toy problem. but we can also show this for something that's a bit more complex and that we've actually done experimentally. So in this case, I'm showing a scan path that was generated to be able to build the Mona Lisa. And the intention here is to get a very different solidification microstructure in the center than around the borders. And if I perform the thermal simulation, here I'm showing what the solidification cooling rate here, which is just the gradient times the velocity. And you can see that we're getting a very significant difference with a very low cooling rate internally, and then a much higher cooling rate around the borders of the geometry. If I extract what the gradient and velocity are, you see that we do get kind of a systematic variation between the competition between existing columnar dendrites versus nucleation of new equiax grains, depending on which of those regions we're in. So now we can take a look at that experimentally, and indeed, the electron backscatter diffraction image shows that we get a very consistent systematic variation in our grain structure between these two regions. So if we take a zoom in first, let's take a look at this central region. You can see that we're getting primarily an equiax grain structure, and we get kind of a weak fiber 001 type texture parallel to the build direction. We can also look at that in cross section where the build direction is now up. And you can see that, yes, indeed, we're mostly getting these kind of randomly oriented grains, though every once in a while we'll encourage, a few grains to grow across multiple layers and give us this kind of weak texture. If we take a look at this outer region, it's a little bit more complicated. It turns out that we've kind of got two textures that are stacked on top of one another. One is a fiber texture that's located at the center of the melt pools, and then the other one is a 011 type texture that has this kind of hexagonal pattern that's actually related to the grid of these spot melts that we ended up using for this scan path. If we take a look in cross section, you can see what's going on here, which is that along the center of our melt pools, we get these elongated grains growing up along the build direction. But then in the overlapping regions between melt pools, we have a tendency for these spots to kind of alternate between different layers, and that encourages growth of the symmetry 100 or 010 type dendrite directions to grow upwards in alternating ways, and that encourages this 011 type texture. And this kind of effect has been shown in other alloys and other scan paths as well. So by varying this kind of scan path between these different regions, we're able to achieve this kind of systematic variation in grain structure, even for very complicated geometries. Now, the disadvantage of the approach that I've shown before is the way that we're generating those scan paths has a lot of heuristics that are just based on intuition from whoever's trying to develop those scan paths. So we're also working on some techniques that are a little bit more automated. We published a paper a couple of years ago where we used a genetic algorithm to generate scan paths. And that works reasonably well, and there's some ways to encode some high fidelity model information into this. However, the genetic algorithm is quite expensive, even if you're using these simplified models. So more recently, one of my colleagues, Jamie Stump, he's got a paper that's in press at Computational Material Science right now, where he's replacing some portions of that computational model with a fully convolutional neural net that makes a prediction of what type of microstructure you're likely to get. And then we can use various type of optimization algorithms quite efficiently. In this case, it's a simple greedy algorithm to be able to generate new scan paths. And we can get some pretty sophisticated behavior in the scan path that's able to modify the equiax fraction in this case. Again, we're just using Inconel 718 as kind of a toy problem. So this is where I kind of think the future of this type of scan path optimization stuff is going. But I want to take a minute to actually talk instead about a different approach entirely. So another approach that allows us to address this problem of microstructure control is to look at it through the lens of alloy design. So really, microstructure design and microstructure control is the intersection of the processing window for a given alloy for a given process, in this case additive, against the kind of variation in processing that gives you a meaningful variation in microstructure. So you can think about addressing this problem by trying to expand your processing window through unique scan patterns, which we talked about before. But you can also approach it through trying to change this microstructure and processing space through changing your alloy composition. So rather than work on conventional alloys, we can design new alloys specifically made for this purpose. But what do you need for such an alloy? Well, you need it to have attractive properties so that people want to use it for some kind of application. You want it to have the widest possible processing space, and you want its microstructure to be sensitive to those processing conditions. So what kind of alloys can we possibly design that might help us with this particular kind of problem? So for this, I'd like to do a case study on designing aluminum alloys. So this is kind of the problem statement. There's two things that we're interested in as far as aluminum alloys go. The first one is this hot cracking problem. So many of our conventional wrought aluminum alloys are very prone to hot cracking. However, they also have very attractive properties. So if we try to process these alloys with additive manufacturing, it turns out that we have a tendency to form these cracks and we can't access this property space. On the other hand, we can process things like aluminum silicon alloys that are very castable and resistant to these kind of cracking problems, but we can't get the same kind of attractive mechanical properties. At the same time, we're also interested in trying to push the temperature capabilities of aluminum alloys. So most of these wrought alloys are precipitation strengthened, and when you heat them up to put them into service at elevated temperatures, you have a tendency to dissolve your strengthening phases, and that leads to a decrease in your strength. So there are a couple of alloy systems that have started to being adopted, like aluminum scandium. However, these tend to be expensive and they don't give us this kind of elevated temperature properties. So I'm going to propose a different way of trying to go about alloy design, and we'll show how this also overlaps with our microstructure control. So we ended up looking at the aluminum cerium copper system. And the reason for this was we did some initial computational thermodynamics calculations, and we found that this ternary system exhibits this kind of eutectic reaction that I'm showing here on this Shiloh simulation that gives us a very flat temperature response with respect to the solid fraction in this critical range where hot cracking is the most susceptible. And we are able to do some simple approximations for our hot cracking sensitivity. In this case, I'm showing a calculation based on some work by Sindo Ku, and that shows that the sensitivity of this particular alloy composition is quite low compared to some of the conventional wrought alloy compositions or even against aluminum silicon. We can also plot out what that hot cracking sensitivity is across the composition range for the ternary system and select a particular alloy chemistry that we think gives us a balance of processability and mechanical properties. We also decided to add some zirconium to this alloy, the reason being that it acts as a grain refiner that gives us some equiax grains that are also help us resist hot cracking problems. Also, it means that we'll be able to heat treat this alloy later to form L12 particles, which are good for high temperature strength, although I won't spend very much time here talking about that. We then produced this alloy and we fabricated samples across a range of processing conditions. We were able to show that it was very processable, giving us a maximum density well in excess of 99%. And then we were able to measure these properties. And again, I'm showing this yield strength versus elongation graph with aluminum silicon as these gray data points down here in the bottom left, and these colored points being wrought alloys in the top right. And you can see that this alloy is now both highly processable and gives us mechanical properties that are competitive with some of our conventional wrought alloy compositions. So what does the microstructure look like? So it's predominantly eutectic. So here's showing an example of these kind of eutectic networks that we see in an aluminum copper cerium based alloy. And the interesting thing about this is we can take, at least to a first approximation, relatively simple model for the microstructure as a function of our solidification conditions, in this case proposed by Jackson Hunt, which basically looks like this, saying that the spacing of the intermetallic particles in our eutectic will be inversely proportional to the square root of the solidification velocity. And our solidification velocity is going to be somewhat proportional to our laser velocity. So we expect that this will affect kind of Orawan type strengthening in our alloy. So by changing this velocity, we expect to get a variation in our mechanical properties. So what our hypothesis is here, that by increasing our solidification rate, we can promote an increased as fabricated strength. And because we've got an alloy that's designed for excellent printability, we should be able to achieve a very wide range of solidification conditions. So if we take a look at this experimentally, we see the type of microstructure that we get at different sets of processing conditions. And so you can see that if we go from 2000 millimeter per second laser velocity to a different set of processing conditions with 5000 millimeters per second laser velocity, we get a pretty significant refinement in our eutectic structure. We're able to quantify that by characterizing the microstructure for different sets of processing conditions. And then we can also look at the mechanical properties, and I want to draw your attention to kind of the open squares here, which is showing that our yield strength is increasing as a function of scan speed in the horizontal direction. You see that there is also some changes in the anisotropy here. That's an interesting detail that I'm not going to spend time going into here. We're working on a manuscript that details this. You can also see that we get a pretty nice hardening response during heat treatment, as well as some variations in the amount of anisotropy in those properties. But I want to focus on this here, where we're seeing that our strength is clearly a function of these processing conditions. And so then what we did is we took a look at some specific sets of processing conditions and measured the hardness. And we see that there's a really significant and systematic variation in the hardness as a function of our scan velocity. And we can relate that back to that variation in our eutectic spacing. We can then take various sets of processing conditions and put those into a single component. And that allows us to get this very consistent variation in hardness from one end to another of a sample. And the only thing we're doing here is changing our process variables. Keep in mind that there's no complicated scan path optimization that's required. So finally, I'd like to show kind of a complicated geometry. In this case, we're taking the MDF logo as an example, and we can simply put two different sets of processing conditions in these two different regions. And if we fabricate this and perform a micro hardness map, you can see very clearly that we get a systematic variation in our hardness between these two regions that's associated with the variations in laser velocity. And we can also perform the statistics on this and show how much of a variation that we get. So here I'd like to conclude. Basically, what I think we're able to show is that the spatial distributions of microstructure can be effectively controlled in additively manufactured components. And I think that that's an important tool for us going forward to be able to create very high performance components using additive manufacturing. Using conventional alloys, usually we end up having to resort to these novel scan paths to be able to realize those advantages of this kind of approach of controlling the microstructure. And in order to do that, I think it's really important that we have these reliable, lightweight computational models that we can use directly in these optimization processes to be able to generate these types of scan paths. However, it's something I think is really interesting going forward is that it is possible to design alloys specifically for additive manufacturing that give us these very beneficial performance metrics, but also enable us to control the microstructure in a simple way so that we could easily start implementing these things and hopefully pushing it out towards industrialization. I had a pretty large team of people that was helping me. I've got kind of an incomplete list of acknowledgements here of various individuals that have helped in different parts of this project. And lastly, I'd like to thank some of our funding sponsors. This work is the combination of a variety of projects funded through the Exascale Computing Project, as well as the Department of Energy, the Energy Efficiency and Renewable Energy Office, as well as the Office of Electricity. And a lot of this research was performed at the manufacturing demonstration facility at Oak Ridge. Thank you.